Unfortunately, to understand the Adels, we have to consider differentials, which makes look Adels like a nice number, like a 5. so that's the last like a non-pleasant part in the code. Okay, that's the last completely abstract thing, and afterwards I think things are now like in a sense they get more complicated because you do Galois and stuff, but they are much more intuitive. That's what I'm saying. Like technically they are more complicated, but you know what's going on. You know what you're doing. Maybe it's difficult to prove what you're doing, but you know what you're doing. So psychologically speaking, you don't feel like you follow a line by line. That's what I'm saying. But the next unit is Weil differentials. Weil differentials. Differentials. And the thing you should note is the first word, Weil. Right? So differentials, you imagine what it is, like a dx or something, right? And you integrate or stuff like that. It's something that you feel like now I can use my geometric intuition. So Weil differentials is in a sense, it's like an abstraction of an abstraction of that. Seriously. So in chapter 4 of Stichtenov, which I'm not covering, there is an abstraction of differentials, and it's actually very nice to see. You do it in the seminar. It's really fun. So you really kind of understand what the physics did when you do the dx over dy. You can formally define that and do things like that, and it's very abstract. And Weil differential is an abstraction of that. So I'm going to prove things about really this space. That's what I care about most now. But in order to do this, I'm going to use something which I'm called differentials, and it seems to have nothing to do with differentials. So that's going to be like that for 2 hours, and that's what's going to happen. And, but know that there is an intuitive, that there is a way of connecting this to the more intuitive abstraction of differentials. And actually, in the notes, I have some attempts to do that, but last time it didn't work. So I'm not going to do it. And some of you, two of you probably will take chapter 4. It's an easy chapter, actually. It's kind of easy. That's what's annoying. I can do it easily, but then we'll get to the important parts. So I'm going to use this notion called Weil differentials, but don't have high hopes about seeing like differentials. Okay. Anyhow. So what's the philosophical thing here? So I really want to understand this object. Turns out this is the right object to understand the deficiency from the deficiency. And if you want to understand an object, especially in algebra, but generally in mathematics, the way to do so is to look at functions from that object to something. Like all of what we are doing here. We want to understand the curve, we look at functions from the curve, and so forth. So these are differentials. So, but it turns out these are actual differentials in the proper sense that you think of, even though you don't think of Adels at all. So what I'm doing is that, okay, so let me just write the definition. So definition 1, Weil differentials, written here. So, okay. So say our function field. A Weil differential, Weil is someone, right? It's a very famous guy. Differential, it was a street named after him in IS. Exciting too. Anyhow, is an element omega here. So what is this? These are all linear functionals from k-linear functionals from A to K. Right, so just to remind you, this is a notation that's usually used. These are all, maybe I have it just to, yeah. So, right, so, right, so maybe not the best name ever. I'm just worrying about the name. alpha. Let me not, yeah, put it there or something. Good. So, okay. This is a general. So, home K of AK, it's a famous name, sorry, these are all K linear maps from here to here. But since the target is K, these are called functionals, like you go back to the base field or base K vectors base field. So you look at all linear K linear maps from A to K. This is what it is, that's it, nothing more. Homomorphism. Like, right, so f of A plus B is f of A plus f of B, and f of C times A, when C is in K, is C times f of A. Like in vector spaces, like nothing weird here. Yeah. You can't integrate, but you can do residue stuff. But we are not going to do it. In the seminar, you can, and you will, but not here. It's crazy that the residue theorem is true. And we are kind of hovering over it right now. We're talking about it. No. I didn't state it. The residue theorem, in complex analysis, you know what it is, right? So it's, when you integrate over a contour, then what you get is the sum of poles, like this thing. And here you don't have a contour, you don't have an integration, but that's still true. So weird. Anyhow, don't worry about that. So good. So this is a Weil differential, just a K-linear map from A to K. Oh, maybe that vanishes on. There is an important that vanishes. Oh, that's the whole point. Vanishes on some lambda A plus F. Yeah, I just erased. So what we care about. Sorry, let me just write it again. So what we care about is this set, this K vector space, because its dimension is exactly the deficiency of the deficiency, whatever. And to understand it, we want to understand linear functionals from it to K, linear functionals, or put differently, we want to understand linear for a given A, right? So instead of understanding linear functionals from this quotient to K, it's better, it's kind of simpler to understand linear functions from A to K, which vanishes on this. It's the same thing because these are the cosets, so you need to, if you want to understand the behavior on the cosets, it's enough to understand the behavior of functions from here that vanish here. So, this is just a motivation. The actual definition is a Weil differential is any K homomorphism from the Adels to K that vanishes on some, there is no A here, there is some divisor A for which this vanishes, your linear map vanishes on this space. No. There exists an A divisor such that this holds. It can vanish on some other points, right? Like as long as in its kernel you have something like that inside, right? Not only right. That's a good point. And take like can we also like say and let it be the right? Yeah. So we are going to define that soon. This is going to be we are going to need us to know who is the A that because of which omega is a differential, but not in this general definition. Good question. So yeah, you would think you first start with that and then do this as a union or something, but you do it like that. So yeah, so maybe we'll end with a technicality, and then next time we'll continue. Actually, it's a good point. So we have this definition, we have a technicality, and then we'll continue next time. What is a set? Lambda? You have to get used to lambda. Lambda. Right. It's a set of Adels, and I want. Yeah, because that eats Adels, right? So omega gets as input an Adel, and I want it to, and it outputs a number in this field. So I want it to be 0 on all of the Adels of this. Contains this. Right. 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 So you want that there exists an A such that kerr omega contains lambda A+F. Exactly. But not necessarily equal. Maybe I should put that as the definition. Good. So a technicality. So yeah. So generally speaking, so say, just not to confuse you, say V, okay. Okay, let's do it. So let f over k be a function field, and f is an f vector space. Okay, you have, and V is an f vector space. You have a vector space over V, functions, not of, and W is a k vector space. Okay, so V is a bunch of functions, and W is a bunch of field elements. Okay, so we know that from KVW on all k-linear functionals from V to W, right? V is an F vector space. It's certainly also a K vector space. So you can talk about these things. So you look at all K homomorphism from V to W, we know that this is a K vector space. Right? If you take K functionals, you can add them up, you can multiply by a scalar, everything's good. And you completely ignore the fact that V is also an F vector space in doing so. Right? Just you only work at the K level. What we are going to do is to work at the F level. So what I'm saying is that actually from KVW is an F vector space. Namely, okay, adding elements from here is the same, but there is a way of multiplying a homomorphism from an element of F, not just from K. I need to tell you how to do it, but there is a way of doing that, and it extends the usual multiplication from K. So here is how it works. So you give me A from F, and you give me phi, and my job for you is to tell you how to define A phi, the functional A phi. So I want to define it. I want to prove that this is, like, give the definition of this defined product properly by scalar, a larger scalar from F, such that this will hold. And what would you do? So A phi should take something from V, right? And I should tell you V is from V, and I should tell you what to do. And you only have phi. Exactly. And that's it. That's what you do. So like a function times phi evaluated at element V is, this is a vector space over F. So you can multiply it with V. This is a vector over F, but this is element F. So you can take the product, put it here, and apply phi. And that's it. That's how you do it. And you technically need to show stuff. You need to show that, A phi, you need to show it's a homomorphism. So you need to you need to show that sum is okay, like A phi of V plus V prime is the same as A phi of V, but that's the same, that's fine. And you also need to show, that's kind of more fun, to show that A phi of BV, where B is in K, you need to show that is B times A phi of V, and I will leave that pleasure to you. It's like 2 things to put here. It's just easy. We can do it. So by definition, it's phi of ABV, like this. But then, right, the types are difficult. This is in F, this is in K. So you can more interesting part of the course, the extensions, not just understanding a function field, but understanding function field extensions. Okay, yeah. So see you next time.